Welcome once again to our course. So in the last class we have discussed that how the stereoregularity is possible using the two well established pathway, that is the catalyst site control or chain end control. So we have discussed that by using the chiral catalyst we can get the selectively one isomers, or even though we are not using the chiral catalyst, even though the stereoregularity is possible, where your last inserted monomer dictates the stereoregularity for the second insertion of the monomer. So with this concept, what we learned in the last class, we will try to discuss the olefin polymerization by Zeigler Natta catalysts, and what are the important features, what the factors influencing its stereoregularity. In the last class, if you remember, we have discussed the very simple mechanism of bond forming, bond making by the using of Zeigler Natta catalyst, and now today we will try to understand how it tunes its stereoregularity, what are the sites, what are the mechanism. Okay, so it should be really interesting. So as I told, we will try to understand the mechanism of Zeigler Natta polymerization and origin of the stereoregularity. Okay, so what is Zeigler Natta catalyst? All we know, it's a widely used catalyst in industrial polymerizations, very popular, and you know that Nobel Prize is awarded for this remarkable discovery. The system, catalytic system, is mainly TiCl4, and the transition metal is titanium, and you need another metal, that is the aluminum. So it is basically the titanium aluminum system, the heterobimetallic system. So this one is the catalyst and this one is the co-catalyst. So the catalyst and co-catalyst are both needed to initiate the polymerization, and the most of the general Zeigler Natta catalysts are either TiCl4 AlEt3 triethyl aluminum, or the TiCl3 diethyl aluminum chloride. It's a heterogeneous system, and the polymerizations are performed in hydrocarbon solvent. Okay, and the polymerization here, the preferred monomers are the non-polar alkenes. So here what is done, the catalyst and co-catalyst are reacted in the same condition, same solvent, and then monomer is passed. So it's in situ reactions. First the co-catalyst formation and then the polymerization. Okay, so these are the basic steps. You will see here the titanium chloride NL3 that forms the TiCl3R. We will discuss how it is formed and why it is important. So this R is basically the active catalyst. Okay. Similarly, if you can use dialkyl aluminum chloride, you will get the TiCl3R. So these are the active catalysts. Okay. Now let's try to understand little more depth. So this one you will see that you have TiCl3, okay, as you see in the last, okay, TiCl3R, TiCl3R. So you have titanium, you have R group here, okay, and this one 3 chloride, and this is the co-catalyst. Here you have AlR2Cl, okay, and this is TiCl3R moiety. Okay. So most of the active site, the catalyst, co-catalyst sites are generally if you see the discrete structure, it looks like that one. So in the later part we will discuss that this is what we are drawing on the paper. It is not simple. It is very complicated structure. It is a three-dimensional structure, and it is not a discrete molecules as you see from on the pen and paper. We'll discuss and we'll try to understand that how it is important and to realize, to understand, and how the stereoregularity is maintained using the Zeigler Natta catalyst. That's why this catalyst system is very popular. Okay. So not only the TiCl3, we can actually use the other halides also. Okay, like titanium bromide or the mixture of the other alkyl and halides like that. Okay, so but mostly in industry it is used this system. That is the more popular system. So as now you are all aware that this polymerization is the Zeigler Natta polymerization catalyst is famous for getting the stereoregular polymer. So this is you get the isotactic polypropylene. All we know, okay, that what is isotactic polypropylene. So this, if you are all are same, okay, side, then it is isotactic. Okay, we discussed, okay, this one in the earlier classes. Now question is how. Okay, now very interesting. So in the last classes we discussed that we have to use the chiral catalyst. Okay, so to induce the stereoselective reaction, that is goes through the catalyst site control mechanism. And here another way is the achiral catalyst, that is the chain end control mechanism. Okay, now what do you suggest, whether this polymerization is using this is catalyst site control or the chain end control? That is a very interesting question. Okay, and how will answer, whether it is a CSC or whether CAC. Okay, let's see. Okay, what is actually real pathway? That is the very interesting and quite complicated also, that how this Zeigler Natta catalyst plays the role for the maintaining the stereoregularity in polypropylene, either through the CSC or the CAC. As you see that we are using the TiCl4 and AlR3, and what we are getting? We are getting TiCl3R. That is the simplified discrete catalytic, you can say active, to designate the active catalytic site. Now from here it looks like it's a achiral catalyst. Okay, but I'll prove you no, this is not a achiral catalyst, this is chiral catalyst. It's very funny, no? Let's see how it is possible. Before that, we should try to understand how these Zeigler Natta catalysts have been developed, because answer is hidden there. Okay, either it is chain control or the site control. Okay, so let's try to understand. So as I told, this is a bimetallic system, titanium aluminum system. Okay, now this is the titanium aluminum based initiator used for olefin polymerization, especially for to make the stereoregular IPP polymers. So, Zeigler, what he did, he charged the TiCl4 with AlR3 in hydrocarbon solvent. Try to understand what I want to tell, because the answer is hidden. Hydrocarbon solvent. Okay. So, and then he did the polymerization, and he got the IPP polymerization. And so what he did, he prepared the in situ preparation of active catalyst. It is not that first the active catalyst formed, isolated, and then it is used for the catalyst, not like that. Okay. Later, Natta realized that what is formed first, actually it is first formed the TiCl3 moiety. Okay, TiCl3 moiety. I am not considering the alkyl part. And this TiCl3 can exist in different crystallographic form, different crystalline form. Alpha, beta, this is called the crystal phase. Alpha, beta, gamma, delta. So this is this TiCl3, and then it is doing the polymerization, and the color of this one is actually the brown in color. Okay. So after that, Natta was trying to make a different, okay, trying to establish the different routes by reducing the TiCl4 like aluminum or hydrogenation, or using other aluminum derivatives, okay, to make the TiCl3. And he saw that most of the cases he is getting the same brown color. That means is all actually the beta TiCl3, and there is no much improvement, okay, in stereoregularity, okay, or stereoselectivity. But later it was realized that if you take other form alpha, gamma, or delta TiCl3, which are violet in color, all the three forms are violet in color. Okay. So these are the other crystalline phase. Okay. So these are violet in color, and a surprising result was observed. What was observed? A dramatic increase in stereoselectivity. So what we learned from here? We learned that the crystalline phase is important for this case where the stereoselectivity is concerned. Not only that, there is other very complex reactions are operated. We have to consider. As example, what I will list now, set of complex reactions. So what you see, as I told, that we write TiCl4 AlET3 or AlR3, this we write in a very simple way, but the catalytic system is very complex. Okay. So, set of complex reactions I list out. This is basically based on the alkylation and the reduction of transition metal component, that is the titanium. Okay. So, let us see what are the possible reactions when you are charging the TiCl4 with trialkyl aluminum. Okay. So, TiCl3 R plus AlR2 Cl. So, it is basically exchanging one chloride with the R of the aluminum. Okay. Now, again it can react with this one AlR2 Cl and form the TiCl3 R plus AlRCl2. Okay. Now, this TiCl3, that is the R, can react with AlR3 and form the TiCl2 R2 plus AlRCl2. Okay. These are all possible reactions and it actually happening. Okay. Then TiCl3R is reducing and forming the R dot. Okay. And TiCl3 plus again AlR3 is forming the TiCl2R plus AlR2Cl. This R can undergo the recombination and with R dot and forms the corresponding alkyl. Okay. So, no need to be worried about so much reactions. Okay. Actually, we don't need all this information to understand the reaction mechanism, but what I want to give the information that in the reaction mixture there are possibilities, there are a lot of complex reactions possibilities are there, and here you will see that we will be more interest for this kind of species like this one. Okay. Why we will understand from the next slides, where we will be discussing the mechanism. So, you will see that the catalytic system is really complex in nature. Okay. And we will see, although no need to be worried for all this set of reactions, what I am trying to tell that this species TiCl3R, okay, try to concentrate on this one. Okay. Let us see what happens. So, here, although as I told that this we write as TiCl3, okay, but it actually not simple as that. So, it is a discrete polymeric kind of form where these chlorides are shared by another titanium. Okay. So, in like this one. Okay. Here you will see this titanium and this chloride is again shared by the another titanium. Okay, like that. Okay. So, different active. So, this is actually the active center or rather you can say active catalytic center, okay, where you will see there is a one vacant site, okay, and um, all the chlorides are basically shared with another titanium, okay, and one vacant site, and one alkyl group, okay. So this is important to understand. So on the titanium, if you just think as a discrete single molecule, so 4 chlorides which are again shared by another titanium through chloride bridging, and one site is occupied by alkyl and one is the vacant site. And this this active site is proposed by Kose, and as I told, is a very complex system. So different mechanisms have been proposed, or different active centers has been proposed time to time to understand its stereoregularity, polymerization, like Boer 1979, Carrick 1973, Cardidi 1989, Kose 1967, and so on. Okay, at least 10 mechanisms have been proposed, but this is the most well accepted, easy to understand, and this polymerization is well understood by this mechanism proposed by Kose Ullmann. So let's see what is that again. So now it is clear that how this Zeigler Natta catalyst looks like if you consider as a single molecule. So here the picture will be more true here. Here, as I told, that these chloride are shared again through the titanium chloro titanium bridging, okay. And if you see these molecules, this actually the crystal structure of alpha TiCl3, and how does it look like? You will see that I will come, this is the alpha, gamma or delta, as I told, beta are possible. This is the alpha TiCl3. Here you will see this is the titanium, okay, and this is the chloride, and most importantly these are the vacant sites if you see in the crystal structure. And you see here one very interesting, okay, very interesting. So this one, if you this plane, you see this is a relationship of enantiomeric. So here you see, so this is the called enantiomeric phase, okay. So why it is important? It is important to understand that there is a chiral center exists, and that chiral center actually depends on the what phase you are using, the percentage of the chiral center, whether it is alpha, gamma, beta and delta. You see this moiety carefully. This is basically enantiomeric catalytic phases. Now it is understandable that why these catalysts actually act as a chiral catalyst, okay, fine. So here, so that's why, so it is always better to consider as TiCl3 as Ti2Cl6, which will give a better picture of the Zeigler Natta catalyst, and also this has been supported by molecular mechanics calculation. Okay, so now I am sure that you are you understand that what are the possibilities, okay, in the simple TiCl4 ALTT system by pen paper, but actually it's not that simple. It's very complex structure. Now with this concept, let's discuss now what is the real mechanism is operated here, okay. Why it is isoselective? Why we get the isoselective or isotactic polypropylene? Okay, so see this slide, this one is very important, so please see it very carefully and try to understand. So this is the active center of the Zeigler Natta catalyst, as we discussed in the last slide. Here you will see. So this is this one, considering a single discrete molecules. So what is happening now? You will see that the propene coordination, simple. Okay, so this is the vacant site. Propene coordination is happening, and as we discussed in the last class, the bond breaking, bond forming steps. So after coordination, there is a 4-member transition step, and then what happens? You will see there is a migratory insertion reactions. So here you will see that there the polymer chain is now migrated here. So now what is happened? This is my vacant site. Be very careful. So my vacant site was here, but now the vacant site is here. So you will see the position of the vacant site is now changed. So it was initially, if you see that, if you check this chloride, so it was vacant site was cis to this one. Now the vacant site is trans to this one. Okay. Now if the vacant site is positionally changed, now if the alkene coordination happens here, then definitely there will be no isoselectivity, because isoselectivity will happen where the addition of the next monomer will also happen on the same vacant site. Then only it is possible of isoselectivity. If not, then it will be symbioselective. So here what is happened? You will see that in this step, this polymer chain is migrated, and here basically not the whole polymer chain does not be careful here. The whole polymer chain does not migrate, okay, but only the active end, migrates, okay, according to the principle of least nuclear motion. Least nuclear, that is the less energetic pathway. Okay. Now you will see that now vacant site is in a different position now. So what it is proposed, that there is a back flip. That means this chain, okay, now is again went there. Now you will see that the vacant site was here initially. Now the vacant site is again at the same site. Okay. So this is called the site epimerization. Okay. So migratory of polymer chain at the same position. So why it is happening? Back flipping, the migration of polymer chain at same position. So here you see that here my polymer chain, and now here is my polymer chain, but the length has been increased by 2 carbons after insertion, obviously, but my vacant site is now at the same position as it was in the previous step. So this is the mechanism for the isoselective polymerization. Okay. So this is the mechanism for catalyst site control of isoselective polymerization, and which are the well accepted by to explain the isoselective polymerations, which actually operated by the catalyst of Zeigler Natta, where you see that it does not look like a chiral catalyst, but actually it acts as a chiral catalyst. So, what are the basic steps for isoselective polymerization? Regeneration of the original configuration with vacant site. This is very important. Otherwise, if it is not, then we will get the syndioselective. And preference of the same phase of propene monomer when we are putting the vacant site a particular position. Okay, let us say this is my catalyst, here is the vacant site. Okay, so if we create the vacant site after one addition of my monomer, then after insertion the vacant site should be same, okay, so that the monomer can approach through here, not like through here or here, then it will be not stereoselective. Okay, fine. So, but as you see, the polymer, the catalyst, okay, is it very difficult to understand, okay, how this chiral environment is formed, okay, and because this is a heterogeneous system, okay, this enantiomeric phase, this is a heterogeneous system. So, this all the polymerization actually happens on the surface of the catalyst, okay, it's not a homogeneous system. So, polymerization occurs on the active site of the crystal lattice, that is on the surface of the solid, and this active site influenced by electronic and steric environment, and that's why we get the different rate of polymerations depending on the where is the vacant site is. And as it is a heterogeneous system, the active centers can occupy a variety of lattice sites, and as a result of these 3 points, most of the polymers achieved from Zeigler Natta catalyst is actually the broad molecular weight distribution. Although these are isoselective, but we get the broad molecular distribution because due to its heterogeneous system, okay, because this attack of the monomer actually depends on the active centers, how the vacant space is available on the surface. So, to understand in more detail about the stereoselectivity, some of the factors we have to understand, otherwise the discussion will not be complete. So, we know that beta TiCl3, which is the brown in color, has quite less stereoselectivity, okay, and compared to the alpha, gamma or delta TiCl3 has much more stereoselectivity compared to the beta TiCl3. Okay. So, this is, as I told, this is violet in color and this is brown in color, okay, and this is the high stereoselectivity and this is the low stereoselectivity, okay, and I will try to emphasize that what are the factors for observing this kind of difference, okay. So, I will not go in detail on solid state. If you are interested in the solid state properties of the TiCl3, you can further study the related topic, but what I will try to explain, I try in a very qualitative way that what are the factors for governing the different crystallinity and how this dictates the stereoselectivity. So let's try to list out. Gamma TiCl3, here the chlorides in cubic closed pact. Okay, these are actually the layered structure, and the alpha TiCl3, the chlorides in hexagonal closed packs. Okay, and delta TiCl3 Cl minus in mixed hexagonal and cubic closed pact. Okay, and in the beta TiCl3, that is quite different. The here is actually the, if you see the solid state structure, it's a bundles of linear TiCl3 chains. So in this case, what happens? In this case, half of the titanium atoms have two vacant sites, and here half of the titanium atoms have one vacant site. Okay, now you try to understand from this structure here. Okay, so in this case, this is a structure of alpha TiCl3. Here you will see one vacant site is a layered structure. Okay, but in the beta TiCl3, that is a linear TiCl3 structure, and here two vacant sites are possible for the half titanium, and for the half titanium it is one vacant site. Now you can imagine, if there is a two vacant site, then obviously there will be no stereoselectivity, and that is the reason, okay, that stereoselectivity is quite less for the beta TiCl3. Okay, now I think it is clear, understandable. So this is the very important factors, okay, for choosing the right system in doing the polymerization in Zeigler Natta. Not only that, we should also know that, like if you use the alpha TiCl3 and if you use TiBr3 or TiI3, okay, the stereoselectivity will be more in the for the chloride rather than iodide. Okay, and also similar for TiI4, it is almost similar for all the cases. So we should, these informations are very much needed, otherwise we will choose the wrong catalytic system if I want to target for a particular polymers. Okay. Now very interestingly, if we use the VCl4AlT3, because these are, you see, titanium, vanadium. Okay, so if we use the titanium, we may think that, okay, if we just replace by VCl4, probably we will get the same polymer, but it is actually not. So you will get the syntactic polymer if you use the VCl4AlT3 system. This is also Zeigler Natta, falls under the Zeigler Natta Catalyst category. So here you will see that all the mechanisms are similar. Okay, similar except one step, except one step. Okay, here no flip. So in the here you will see for Zeigler Natta there is a back flip. Okay, that is the back flip, and here that the flipping, so that no back flipping occurs, and as a result what you are getting, there is the vacant site. Now the vacant site is here, so alkene is coordinating here. Okay, now that's why this vacant site is now not getting getting back at the original position, and that's why we are getting the symbiotic polymerization. Okay, so for VCl4 ALD3, if suppose you want to get the specifically the symbiotic polymers, then you will have to choose the VCl4 ALD3 system, and if you want to take the if you want to make the isotactic polypropylene, you have to use the titanium aluminum system. Okay, so in a conclusion, what we have discussed, the to understand the polymerization mechanism of Zeigler Natta system, the role of vacant site, position of the vacant site, regulating stereoregularity, the role of different catalytic systems of Zeigler Natta category, as example titanium, aluminum, and the vanadium aluminum system. So here you see that for titanium aluminum also very important to understand how the stereoregularity is maintained by using the different titanium analogues, because now we are well understood that the polymerization, the stereoselectivity is maintained by the titanium analog, and more specifically it is due to the different crystalline phase of the titanium analogs. So it is now very clear that how the with one example of the metal catalyst, that is the Zeigler Natta and their analogs, that how the polymerization is quite different than the free radical, radical or anionic polymerization. It is more interesting and more advantageous to have to control the microstructure and stereoregularity in polymer. So with this knowledge, we will discuss in the last class with the Metallocene catalysts, where you will see that the stereoregularity again can be maintained, but where the mechanism is quite similar and more easily understandable, where the Zeigler Natta catalyst, the mechanism is really very complex, and it sometimes it is not very understandable, because it depends on the from the knowledge of the solid state chemistry, and these are also as it is a heterogeneous system, all the polymerization on the surface of the catalyst, so the mechanism is very complex. This is the most advantage of the Zeigler Natta catalyst. Okay, so in the next class we will try to enjoy a different category of the catalysts for the polyolefin polymerization. See you in the next class. Thank you.